Hello, this is the final year product poster presentation for course ENGG 4920C, Information Engineering Department, the Chinese University of Hong Kong. We are Ren Yi and Luan Tianhao. Our topic is implementation of wide bandwidth channel estimation block for 3 users. Generally speaking, in most wireless communication systems, such as CDMA, MIMO, OFDM, etc., receivers need to have accurate knowledge of channel state information to perform demodulation and detection. It means that channel estimation is a crucial part of every transceiver implementation. So in this project, we're going to implement the channel estimation block for network holding multiple access relay network structure. That is the NCMA network for 3 users, including radio. First of all, let me briefly introduce the motivation for our project. Before describing the NCMA system for 3 users, let us first consider a scenario for 2 users. A typical physical layer network coding (PNC) relay network with 2 users is illustrated here in this figure. For the scenario here, user A and user B communicate with each other through a relay R. In PNC, both users are allowed to transmit data to the relay simultaneously. After receiving data from both users at relay R, an XOR operation is carried out before the signal is broadcast. Finally, the 2 users are able to recover the intended signal by doing another XOR operation with the received broadcast signal and its own transmitted signal. This is how a PNC works for 2 users. It is natural to extend the relay network to a system for 3 users, that is an NCMA network as shown here. Apart from the important modulation and demodulation blocks, it needs some other blocks such as synchronization block and channel estimation block for it to work properly. The objective of our project is to construct a channel estimation block that is suitable for the system shown here. And this relay network system for 3 users is exactly the motivation for our project. For the underlying wireless communication technique, we choose the OFDM, that is the orthogonal frequency division multiplexing scheme, as the platform to build our channel estimation block, since OFDM forms the basis for most of the 4G systems and may achieve a data rate as high as 100 megabits per second. Basically, at OFDM transmitter, we take the inverse fast Fourier transform for a bunch of information symbols and add a certain amount of cyclic prefixes before transmitting them into the channel. Correspondingly, at the receiver, the fast Fourier transform is carried out after getting rid of the cyclic prefixes. The detail of the OFDM scheme is out of our consideration here, but we should know that OFDM scheme effectively converts a frequency selective channel into a collection of parallel flat-fading channels, as shown here. As we can see here, inter-symbol interference is successfully removed in OFDM system, and each received symbol depends only on the current transmitted symbol, plus some noise. And these HD0, HD1 all the way to HDN-1 are what we are going to estimate in our project. And for simplicity, we're going to implement something called the zero forcing estimation by simply ignoring the noise and making use of preambles and pilot tones, which are going to be introduced in detail later on. Okay, here is the NCMA system as a whole. Our implemented channel estimation block is shown in color here. It has 3 input ports and 5 output ports. The first input port is the most important one. It receives the endpoint FFT of the received samples in frequency domain. And these are exactly what we are going to use to do the channel estimation. The other 2 input ports are just used as indicators or to do some simple calculations. For the output ports, the first one is just a direct copy of the first input port, and it serves as one of the input ports for the subsequent demodulation block. Then these 3 ports are the estimated channel coefficients corresponding to the 3 users, and the last output port is just a flag used as an indicator again. So this is the whole NCMA system. As we've said before, pilot tones are used in our project, so we have to worry about where to put these pilot tones. There are 3 conditions we need to consider as shown here. First of all, it must be guaranteed that the interestimation time at the same frequency is less than the channel coherence time. Basically, the channel coherence time, TC, stands for the average interval during which the channel does not change dramatically. Assume 2 pilot tones that are placed at the same subcarrier but separated by NL-OFDM symbols. Then these 2 pilot tones can be used to estimate the channel coefficient at the same subband of symbols falling in between if their corresponding channel coefficients are well correlated. Here, sampling theorem is taken as a reference. We construct the symbols in a way such that NL times T is less than or equal to half of the channel coherence time, where T here is defined as the OFDM symbol interval. The second condition we need to satisfy is that pilot tones used for interpolating the channel transfer functions should be well correlated. Basically, this condition is related to the coherence bandwidth and delay subset of the channel. It says that the subbands corresponding to successive pilot tones should be well correlated. In this project, we save the work for interpolation by inserting something called the long training sequence, in which all the samples serving as pilot tones. In this way, we may simplify the computational complexity, but on the other hand, decrease the information rate at the same time. Last but not least, we consider the robustness of our channel estimation block. Remember, we are using zero forcing method, that is, we totally ignore the noise. It works fine when SNR is high, but will blow up the noise if one pilot tone is severely attenuated by the channel. So we distribute the pilot tones in a rhombus type, which is able to diminish the degradation of channel estimator in case of high attenuation. With these 3 considerations about the position of the pilot tones, we implement the real transmission scheme as shown here. In this feeder, every grid stands for 1 OFDM symbol, which consists of both data samples and cyclic prefix samples. For the purpose of clear illustration, we separate the signals for different users into different lines here, but one should be clear that the actual received signal is the addition of the 3. STS here stands for short training sequence, which is used for the purpose of synchronization. Whenever a certain user transmits its STIs, both of the other 2 users keep silent. The same scenario applies also for long training sequences, the LTS, which are used for estimating the channel state information. Notice that both STS and LTS appear before the actual data transmission, so they can also be called preambles in this case. So after the transmission of the preambles, all of the 3 users start transmitting their OFDM symbols for the actual data simultaneously. Also, we have some constraints on every OFDM data symbol, which is shown here. In our project, we divide the total available bandwidth into 64 subbands. Among all the 64 subcarriers, 12 of them carry no data and are used as safeguards. For the remaining 52 subcarriers, 46 of them are used for transmitting information data, and the other 6 are used for transmitting pilots. It is known to the receiver that pilot subcarrier carries data whose value is 1. The purpose of using pilots in OFDM data symbols is to conquer the problem of phase rotation noise. Since there are chances that the channel coefficients change faster than the interval between the 2 long training sequences, the pilots inserted in the OFDM data symbol can be used to update the channel information and therefore improve the performance. That's all for our poster presentation. Just a brief conclusion. The NCMA motivation for our product is studied, followed by some wireless communication techniques and the channel properties. Then the actual implementations are introduced in this video. The codes and thesis for our implementations can be found in the FYP website of IE department. Thank you very much for watching.